let's pretend for a minute that I have two jars. One of them is full of oxygen atoms, not O2, just plain old oxygen atoms. The other jar is full of hydrogen atoms. Okay? Now, I want to make water out of this. We know water is H2O, so I'm going to need 2 atoms of hydrogen for every 1 atom of oxygen. Now, I can't just go in and count, okay, here's 1 atom and here's 2 atoms. That's never going to work. That's going to take all day. What I want to do is just take some oxygen, weigh it out, and then get the right weight of hydrogen and put them together to make water. But here's the problem. Oxygen is a lot heavier than hydrogen. So you can't just take out, let's say, a pound of oxygen, weigh that, say, okay, that's 1 pound. So if I need twice as many, I'm just going to make 2 pounds of hydrogen. Why? Because the hydrogen is a lot lighter than the oxygen. So you're going to have way too much, right? So how are we going to do this? How are we going to just weigh out some oxygen, and then how are we going to find out how much we need to weigh? Well, we're going to use the mole in order to do that. So let's say I reached into that jar or poured out some of the jar onto a onto a scale, and here I have my oxygen. I'm going to weigh it, and let's say it weighs, let's say 3.20 grams. How about 3.21 grams of oxygen? Okay, so I have 3.21 grams of oxygen atoms, and I need to know how much hydrogen should I weigh out so that I have 2 atoms of hydrogen for every 1 atom of oxygen. Well, this is where the mole comes in handy. Because remember, I said that if you look at that number on the periodic table, if you look at oxygen, it's going to say 16.00. Now, your periodic table might say 15.9994, and it's, just more significant figures, which is better. But I'm just going to simplify it and say 16.00. Now, this is a conversion ratio. This means grams per mole. So we can think of this as 16.00 grams of oxygen equals 1 mole of oxygen. And we know mole is just a number. It's just an amount of atoms. So we're gonna use this. So if I have that many that much oxygen, I'm sorry, not that many oxygen atoms. If I have this much oxygen, well, how many atoms is that? Well, let's find out. I could use dimensional analysis, and knowing that this conversion ratio, right, I'm going to put grams on the bottom, which is 16.00 grams of oxygen for every 1 mole of oxygen. Now, I could do this. I'm going to really go in depth here to illustrate a point. Now I could say, okay, in every 1 mole of oxygen, well, we know mole, that's just like a dozen, right? Only it's just a chemist's dozen, which is 6.022 times 10 to the 23rd oxygen atoms, right? So I'm going to plug that into my calculator here and see what I get. Okay, 3.21 times 1 divide by 16.00 times 6.022. I'm going to hit the E key, which is 10 to the 23rd. I hit enter, and I get 1.2082 times 10 to the 23rd. And that is significant to 3 digits, so it's only significant to there. Okay, so we have that many atoms of oxygen. Well, that was convenient. Now we know how many atoms of oxygen we have, and we know that we need twice as many hydrogen atoms. So if we multiply this by 2, this is how many oxygens we have. We need twice that many hydrogens. So I'm just going to go ahead, take that number, multiply it by 2, and I get 2.416 times 10 to the 23rd atoms. And that's the atoms of hydrogen that I want. But I don't know how much that's going to weigh, right? Because we know that they weigh different, a different amount. So I'm going to erase this right here so I could write. Okay. I need to find out how much that weighs so that I could match them up just perfectly. So I'm going to do dimensional analysis again. So 2.416 times 10 to the 23rd hydrogen atoms. Now I need to get into moles, right? Because the mole is the way that I can convert between grams and atoms. So I'm in atoms and I need to go to moles. So how many atoms are in 1 mole, right? Because I'm getting out of this, I put it on the bottom. Atoms, I want to go to moles. Well, that's just the definition of a mole, right? 6.022 times 10 to the 23rd atoms in every 1 mole. That's just a dozen, right? A chemist's dozen. So now I could go on the periodic table and use my conversion ratio. If you look on the periodic table, you'll see hydrogen is 1.008 grams per mole. So I'm going to use that there. Put moles on the bottom because I want to get rid of moles. And I want to go into grams. So I do 1.008 grams for every 1 mole. Now, is that what I want to know? Yeah, I want to know how much hydrogen I need to weigh out. So I still have my answer in here from the last time. That's how many hydrogen atoms I have. So I'm going to multiply by 1, divide by 6.022, hit the E key, 10 to the 23rd, I'm just going to type in 23, right, times 1.008 divide by 1. I hit enter, and I get 0.40446. And that's grams, right? Because moles cancel, atoms cancel, and now I have grams of hydrogen. So we started off with 3.21 grams of oxygen. And in order to get a 2-to-1 ratio of hydrogen to oxygen to make H2O, I only needed 0.404 grams of hydrogen. Now, does that make sense? Well, yeah, it does, because if you think about it, oxygen is so much more heavy than hydrogen. So if you would have started off, grabbed a bunch of oxygen, weighed it out, and then just doubled that weight, you would have ended up with way more hydrogen than you need, because hydrogen is so light. So by using the idea of a mole, we were able to find out exactly how many atoms we had, and then using that we find out how many grams we need. Now this is going to come into play a lot when we do stoichiometry. In fact, this is going to be the key point here. Now I just kind of rushed through this, and if you're having trouble understanding the mole, then you just think about it as a number, and then go through the stoichiometry videos, and it should become you should get a better idea the more you work with it. As with everything in chemistry, the more time you put into it, the better you're going to understand it.